Good morning. This is Tony Minchell, Applications Engineer at Teledyne LeCroy. I've got an agenda for you today. So I'm going to start with a live demonstration, and then I'm going to be going through a presentation. You can see all the subjects I'm going to cover. The live demonstration is basically going to be covering the first few items. So the live demonstration will be covering how to set the line input switches, the wiring for positive and negative, output voltage, parallel and serial mode. So all these are going to be covered in the live demonstration, and then I've got a presentation to add extra details. So the first one is how to set the line input switches. So why am I talking about that? Well, I'm actually going to be talking about that and showing it in just a moment, because it's my most frequently asked question. Okay, so the question which I have had actually numerous times is why my 32-volt power supply will only output 8.5 volts. And it's because the line input switches are incorrectly set. So let's switch over to the video and we'll have a look at this. So just give me a moment to get my video up. There we go. So here's my video. Hopefully you can all see that. So it's not usual to start by looking at the back of an instrument, but today it's very appropriate. So what I've got here is I've got a DMM, which we're going to be using for making some measurements, and I've got the back of a power supply. And what we're going to be talking about initially is the switches at this point here, how to set these correctly. So we'll just get the video camera in a little bit, so we can clearly see what those switches look like. So what you've got here is a couple of switches, and you've got a little table here, and really you just set these switches according to the table. Seems straightforward, but it's often not done. The other thing which is really important is down here when you've got the fuse rating. So if you're working at 100 or 120 volts, then you need to have a slow blow 6.3 amp fuse. If you're working at 220 or 230 volt, then you need to have a 3.15 amp fuse. Very, very straightforward. So let's look at some of those switch settings on some of the other power supplies I've got here. I've got several. So when a power supply is delivered, it's going to look, well, put it on top. There we go. Stack some up here. Move it back a little bit. It'll come with this label on. So this is how it's delivered with this label. And obviously what you need to do is take the label off before you can put the power cord in, but it's really important to read what it says on there. And what it's saying is set the switches. Okay, and there's been confusion sometimes, because if you look here, this switch looks like it selects between this diagram and that diagram, and this switch between that diagram and that diagram. So some people have been really, really confused by this. But basically, you look at those two switches compared to what is in this box, this box, this box, or this box, and set it according to the power line that you've got. Now, when you look at this switch here, my left switch is switched to the right, and my right switch is switched to the left. And when we look at these diagrams here, we can see that this is set to 230 volts. Now that's the standard voltage that our power supplies are shipped out at, because they come out and we ship obviously globally. So we ship into the US market, which is 120 volts, and we ship into the European market, which is 230 volts. So to avoid any damage to the power supply, rather than trying to guess which market it's going to, we set them all to 230. So if actually you live in the US and you get one of our power supplies, then you need to make some adjustments to set it to 120 volts. Otherwise, you'll get my frequently asked question is you'll only get 8.5 volts out of a 32 volt power supply. And that's the reason, because the switches have not been set. We do put these labels on encouraging you to do that. And that's basically what you should do. Read the label, set the switches, set the fuse according to the table on the back, and you're good to go. Other power supplies have other settings. So I've got another one down here. We'll just bring this one up and pop it in the side. And maybe we'll pop it on top actually for the video. pop it on top here, and we will tip the camera up a little bit. And so you can see a switch setting here. And in this case, instead of having two switches, like we've got lower down here, I actually only have one switch. And this is literally 230 or 115. So it's only got two positions. So it's a simpler switch setting. And I have yet another power supply to show you. So we'll just move this one off the top. And we'll bring this power supply up. Ooh. And with this one, you'll note that there's actually no switch settings at all. So this one automatically adjusts, and you've got for 115 or 230, you've got exactly the same fuse. So in here is a 10 amp slow blow fuse, and there's no changes at all needed. So there's no switches in here. So, I mean, the big question, which I'm sure you're going to ask, and actually questions is a good point. If you have any questions, just type them into the question box, and right at the end we're going to do questions and answers. Okay, so why are there no switch settings on this power supply, but there are on these other power supplies? Okay, that comes down to the design of the power supply. So let me get a couple of components in here. So you have two distinct different designs. One of them is called a linear power supply, and a linear power supply has inside it a transformer, which looks something like this. This case is a toroid. It's low frequency, so it's 50 or 60 hertz, and you've got two mains inputs here. Now these two inputs are 115 volts each. Okay, so if I just put it down here, and we'll just change the angle of the camera so you can see it. Okay, so if I take these to 115 volts, and if I connect them serial, so I've got my input on my blue and my brown, and connect these two together, it would be set to 230 volts. Whereas if I were to connect them in parallel, then I'd have it set to 115 volts. So what these switches are doing on here is that they are adjusting the way that the transformer is configured. So you have distinct coils on the transformer. Sometimes you have extra wires because you've got taps as well. This transformer doesn't have taps. It's just got 215 volt, and then you've also got the output voltages as well. Now when we have a look at the top power supply, which doesn't have switches, why is that? It's because it's a switch mode design. And so I'll just put that to one side. So switch mode just takes the mains in and then rectifies that, chops it, and feeds it through at high speed, high frequency into a small transformer. So this is a typical transformer out of a switch mode power supply, much, much smaller. This also covers the subject of why our linear power supply is so much heavier. This power supply here, which is a linear design, you can imagine the transformer. This is 15 VA, so it's a pretty low power transformer here. Imagine the size of the transformer in this power supply, and this is why the linear power supply is so much heavier for the same amount of power. So when you go to a switch mode, you have a much smaller transformer, and it is switched typically directly off the mains, which is why when you have the power supply at the top here, you don't have switches to set the input voltage because it is using a switch mode design. Okay. So now what I'd like to do is talk about wiring the outputs to get a positive and negative voltage. So let's clear some of these things away. And I'll take one of my power supplies here. So I've got a power supply here, and we can plug it in. Making sure, of course, that we've set those voltage settings. Plug it in and turn it on. Power supply is coming up. So when I look at my power supply here, I've actually got 3 sets of outputs. So I have an output channel 1 here, which can go up to 32 volts. I've got output channel 2 here, which can go up to 32 volts. And I've got output channel 3, which is switchable. And in this case, is switchable between 2.5, 3.3, and 5 volts. Add up to 3.2 amps. So those are my 3 outputs, but all of those outputs are completely independent. So if I want to make these channels work together, these outputs work together with positive and negative voltages, what I need to do is to wire up a common line. So what I can do is I can take a piece of wire and I can wire up different terminals to make up a common line. Okay, I can include ground with that as well if I want, or I can leave ground out. I can then connect that to my DUT. And if I have a common line here and connect it to my DUT, I would connect it to the common input, so basically to the power supply common, if you like. If I use ground, then everything will be ground referenced and the DUT will be grounded. If I connect my channels together and don't use ground, then everything will be basically be floating. So anyway, let's look at how we do that. Now I've already done that on another power supply, so we'll just move this one out of the way. Turn it off first. So here's another power supply. Now I've already wired this up. So if we have a quick look here, I've wired a common line through here. So on channel 4 here, I've wired the I've wired the positive to the positive of channel 1, to ground, to the negative of channel 2, to the negative of channel 3. So I guess that the question is, are we going to get a big bang when we turn this on? Actually, we're not, because we haven't wired any of the other half of each pair together. So we've just wired the positives and negatives from different pairs. And that actually gives us, what that does is that when I've connected it to ground, so everything's going to be ground referenced. So when I put this positive, connected it to ground, then this is going to be a negative reference voltage. And exactly the same here. So I put this positive, connected it ground, so this is going to be a negative reference voltage. And then here on this, I've put the negative to ground, so this will be a positive output voltage. And the same here on my last channel, on channel 3, I've connected here the negative, so this will be a positive output. So let's turn it on, let's plug it in, turn it on, and look at some results. So there we go. And there we have it. And I've already played around with this. As you can see, I've wired it up, and so I just turn all the outputs on. So all the outputs are coming on. So what I've got here, if we look at the settings here, I've got channel 1 is set to 32 volts, channel 2 is set to 32 volts, channel 3 is set to 5 volts, and channel 4 is set to 15 volts. So we can see what the voltages are, we can see all the outputs are on, nothing's gone bang, so let's check our voltages. So we've got our DMM, so I'm going to bring the DMM in here. We've got a lot of reflection on the screen of the DMM, so what we'll do is just make a little change to that. What I'm going to do is I'm just going to take the DMM over here, put the handle down, and we'll lay the DMM on top. There you go. And then we can have a slightly better view. And let's take the camera up a little bit. There we go, so we've got a better view. So I'm going to take my DMM, this is set to DC volts, and we're going to measure all our DC volts in here. So I'm going to take my common line, and I'm going to plug that into the front here. It doesn't matter which one, as long as it's any of the ones which are on the common connected. So I'll just pop it here on the end here. So we've got our common line, and then we've got our measurement. Now we're going to measure each set. So the first one I've got here is channel 4. So this is channel 4. Channel 4 is 15 volts. Is that positive or negative? Well, because I've wired in the positive onto the common line, this should be negative. So we put it on here, and we look at the DMM, and sure enough, we've got the negative 15 volts. The next channel, channel 1, is set to 32 volts. So if we connect into channel 1 here, we can see we've got the minus 32 volts as we've got set on the channel. The next one along here is channel 2. Channel 2 is set to 32 volts as well, but it's wired the other way around. I put the common line onto the negative, so when I connect in here, I will get a positive 32 volts, and that's what I've got here on the DMM. And finally, channel 3. So what have we got on channel 3? We've got 5 volts. We've wired our common line in to the negative, so when we put our probe on there, we've got our 5 volts. So that shows how to wire those up. But there's obviously one question which I'm not sure if anybody's thought of, but I'll ask it, and that is that when I'm working with a power supply, I've got 4 outputs here, and that's great, but I can be pretty sure if my power supply's got 4 outputs, my DUT actually needs 5 different outputs. So it's got 15 volts, it's got 5 volts, it's got plus and minus 32 volts, but my DUT also requires 24 volts. So what am I going to do? Am I going to take this power supply, go put it on the shelf and raise a PO for a 5 output power supply or whatever's needed? Well, actually, no, there is a way around that. So what we can do is we can actually take another power supply here and we can put it in alongside. We'll just change the angle of the camera a bit. So we've got another power supply in, and what we're going to do is take some power and put a little bit of power on this. There we go. Just need to change the camera angle so we've got everything in. There we go. Power it on. So how is this going to work? Well, the first thing I'm going to do is I'm going to turn all those outputs off. So we've got no volts on there. Now what I'm going to do is I've got my common line running along here. Let's move these leads, they're in the way. I've got my common line running along, but I can extend that so I can actually run the common line on to this other power supply. So let's do that. So I can add in common line in here. And then I can add this onto one of these terminals here, depending whether I want a positive or negative reference voltage. I could put it onto the black or I can put it onto the red. The red's nearest my hand, so it'll be a negative reference. It'll be a positive reference but negative output. So I just put the wire through there. So what we've done is we've got a 4 output power supply, and we've now extended it to have 5 all on the same common line. Okay, so I've got, this is set to 9 volts at 0.2 amps. That's fine, we'll just use that as an example. We can turn the outputs on, and then we can put our measurement probes back on our DMM. We still have our black cable connected into our common line right at this far end, but we can now make this measurement here, and this should be minus 9 volts. So we connect that in, and sure enough, we've got minus 9 volts. So it's connected into the same common line, and it just works along. So instead of having to go out and find a power supply with even more outputs, because that's what our DUT requires, we can actually strap our power supplies together using a common line to get more positive and negative for whatever the requirement is. Another thing you can do here, which I'll show you very briefly, is that you can measure across. So if we look across channel 1 and channel 2 here, we've got channel 1 which is set to negative 32 volts and channel 2 is set to positive 32. So between these two terminals I should have 64 volts. So let's have a look and see if I have. Whoop. So I'll put one in there and I'll put the other in here. And sure enough, I've got the 64 volts on the DMM. We've just got that in the edge of the camera. There we go. We've got the 64 volts in the DMM here. Okay, so I've got a negative voltage here and a positive. Now, what happens if I measure from a negative to a negative? Because this one's also set to negative. Well, obviously, what we're going to do is we're going to get the 32 volts minus the 9 volts. So what we do is we get basically 23 volts. Okay, so that's the difference between those two. It would make more sense if I put this onto a positive. So I'll put this onto a positive. So I've got 32 volts. I've got 32 volts in here. We just check that. So you've got 32 volts in here. Okay, that's minus 32 volts. And if we connect in here, we've got minus 41. So we've got this adding on to it. And so you can see with those connections, just by extending the common connection, you can add extra power supplies, giving you more power outputs all working together. So if you haven't got enough in one power supply, just link the power supplies together and it works absolutely fine. Okay, now what I want to do is show you how to use your outputs in parallel and series mode. So what we'll do is we'll turn the outputs off for the time being. So we'll turn these off, and we'll turn this off. And we no longer need these which are wired up. So I'm just going to use this power supply now. So I'm going to disconnect the common line. Turn this power supply off and just move that one out of the way. Excuse me while I just rearrange things here. Okay, there we go. Okay, parallel and series output on a power supply. Actually, to be able to do this, I need to move my DMM off the power supply because I need to show you something on there. And so I'll just move this off for a moment. And what I'm going to show you is right down on the bottom here. We can see that it shows here what the outputs will be. So if I set this into parallel mode, the parallel will come out of these two connectors. If I set it into series mode, it'll come out of these two connectors. And I can set that quite easily. Now I could think about doing this via wiring, or I can do it via these switches here. So let's put that back down there. And we can use the DMM to make the measurement. This is common to both measurements. And what I can do is I can adjust the voltage here, and I could turn those up to, for instance, I could turn those up to their maximum of 32 volts. But if I just use this probe here at the moment, I've got 9 volts on this. No, I haven't. Let's turn the output on. And I've now got 9 volts on that. But if I set the two into series mode, Okay, so the series mode lamp has come on. I've got a series load icon on the front screen. And now when I connect it up, I've still got 9 volts. Oh, that's because that's parallel. So I need to go in here for the series. In series there, I've got 18 volts. So my two are now connected internally to give me 18 volts. If I would go into parallel mode, then I'd still only have the 9 volts here, but now I've got twice as much current. So in parallel mode, you double the amount of current that a single output can have. So these two outputs are now connected in parallel, and so this current is added onto the current of this channel, so you end up with double the current output. And when I go into series mode, then the voltages are added together. So these two are linked, so the positive and negative are linked, and so I get double the voltage. In this case, they're set to 9 volts each. I could just easily set one to 18 volts, but I'm just using this as an example. And so what I've got here is I've got my 18 volts, my 9 plus my 9 across the two channels, and you can see that here on the DMM. Okay, so that's quite clear. And I'm going to move on to, let's have a look, constant voltage and constant current. So I'm going to turn this off. So what's the difference between constant voltage and constant current? Okay, so most people use their power supplies in constant voltage. Most of the people I work with, and also myself. I'm always using it in constant voltage. We know it's constant voltage because when we turn on the output here, so I'm going to turn on the output of channel 1. Firstly, we get a green light. Green is the same as the CV, very small writing down here. Let's see if we can get in a little bit closer. So you can just about see this little light here, and it's green, saying that it's CV, okay, constant voltage. If that light were to turn red, then it would mean constant current. And it also says on the screen here, so it says here CV on the screen, so it's in constant voltage mode. Okay, and that's the way it's working at the moment. And so when I make an adjustment to the voltage, so if I adjust the knob here, so the output voltage will change accordingly, and I can set that all the way up to its maximum, which is 32 volts. So we just go over here to wind this up and down to the different voltages I want to move around the different parts of the screen, so I can use that for setting the current and other things on there. Okay, so that's constant voltage mode. What about constant current mode? What happens there? Well, constant current mode means that you set a current and that's what remains. So it's always exactly the same current. Okay, so how does that work? Now I need to do a little bit of wiring to demonstrate this. So we'll just remove these cables here for the moment. And we won't need the DMM for this part. So what I've got is I've made up a small load so we can demonstrate this, and it's not exactly scientific. It's here. What I've got is I've got 3 5-watt load resistors of different values, and I've got a line in here. And what we're going to do is going to connect these together, and what we'll do is see what happens to the current. So first of all, I'm going to turn the output off, and I'm going to connect my cable in here, and now we're going to see what it looks like with constant current. So I just put my cable in to the hole. So my cable is connected up. got my loads here at this point, and I've got these wires on the end of the loads, and this, so the voltage is going to be connected into the end of the loads, and we're going to see what the voltage is on the output. And I've got another little cable here, which I'm going to use on the live side here, plug it in. And then I'm going to take my wires, and what I'm going to do is just touch the live onto the different loads. It'll go through the different loads and we'll see what's happening. Now, what my current is set to, it's set to 200 milliamps. I don't want to set it any higher than that because of my loads aren't really able to handle that much more than that. They're only 5-watt loads. So we turn the output on. Now we've got a fairly high voltage, and we can go in and I want to change the voltage in there up to its max. There we go. So we've set it to its maximum. That's 32 volts. So that's what we're going to have coming out. So when I press the output here, we've got a green light, which you can just about see on here. So you've got a green light on there, and we've got 32 volts on the end of my red probe here. At the moment, the current coming out is no current coming out, 32 volts. So when I connect onto one of my loads, what's happened? Well, I've hit my current output, which is 200 milliamp, and my voltage has dropped. My current my light has changed to CC mode, so I've got a red lamp now saying it's constant current, and I've got constant current marked on the screen here. So what's happening is we are outputting the required current, and the voltage is changing. So as the load changes, so the voltage, so the current will always try and remain at the set level, and the voltage will adjust accordingly. So we just connect up the last one. Okay, so you can see what's happening here. So I've got, again, 200 milliamps at 9.7 volts. Okay, so if my current usage drops, the voltage will increase. Let's just turn that on. So the voltage will increase. So my current has dropped. So the voltage has increased. It's increased right up to 32 volts. Now, obviously, the concern there is that 32 volts may actually damage your circuit. So if it's not drawing sufficient current, you may suddenly find the voltage goes up and damages the circuit, which is not what you want. So what you can do is you can limit that. So what we can do is we can wind down the maximum voltage. And I'm going to put this down at 2 volts, is a bit low. We'll put it down at 9 volts, for instance. Okay, so our maximum output voltage is going to be 9 volts. Our output's already on. I forgot to turn that off, but our output's already on. So when we connect up here, what happens? We're still in constant current mode. So we connect up and we get our 4 volts, and we get our 200 milliamp limit, which is what we've set up here. We get 4.4 volts. Connect up our other load, and we've got 200 milliamp limit, and it's down to 1.67 volts. And now we connect up our other load, and actually this load is quite low, so it actually doesn't draw sufficient current, so it doesn't draw the 200 milliamps. But what we've gone is we've switched into voltage mode, and we've been limited by our voltage. So when using constant current, you can use the voltage settings here to stop getting voltage so high that it damages the DUT. Okay, so that's it for the live part. There's some, I'm going to go back to the presentation, and then, so I'll be expanding on this. We'll cover these subjects again, and I'll add some extra detail to those in the presentation. So we'll just turn the output off, and we'll just power off the instruments. We'll go over to the slide presentation. And we'll just set that into presentation mode. And just swap the displays over. Okay, so here's our agenda. So we're into the presentation, and let me get a pointer up. There we go. So we're going to cover first of all how to set the line input switches. Now we've already seen that in practical terms, but let's look at it from the slide presentation point of view. So this particular slide and the one afterwards actually came about because of the frequently asked questions. So I've had this frequently asked question quite a few times. So my 32 volt power supply will only output 8.5 volts. Why? And this happens because of the line inputs selector switches. So they're set to 230 volts instead of 120. And we ship them that way, as I said before, because we're never sure whether they're actually going to go be delivered to the US or to Europe. So therefore, for safety, we set them to 230. Okay, so there's the switches, and it's important to realize that this switch here is not switching between these two diagrams and this one between these two diagrams, as actually some confusion by somebody actually came through to me and couldn't understand. They thought these switched between the diagrams, but no, these two switches are switched into either position 1, 2, 3, or 4. The other thing is that there is a label on there, so obviously when you get it, make sure that you read the label and understand exactly what it says, and it's just saying set the switches. And then set the fuse appropriately. There is a little table on the back of all of the power supplies telling you what fuse rating you should have set for the different voltages. And the different power supplies, there's different families between the linear and the switch mode, etc. They have slightly different settings. In this case, we only have a switch between 230 and 115. It will be fine at 220 volts. It'll be fine at 110 volts or 100 volts. It'll work absolutely fine. What you also have here is the fuse rating down here. And when it comes to change the fuse is sitting right here under this little cover, and exactly the same down here. So this is where your fuse is, and you can pop it out by popping a flat-headed screwdriver down the side here, and you can then lever that out and then swap the fuse. It's straightforward. So linear power supply designs tend to have quite a lot of settings. So you'll tend to have one switch here which will switch the main windings, and another switch which will switch the taps, and we'll be looking at that shortly. And obviously you need to read the fuse table to know which fuse to have in there. Okay, so when setting these, never make the adjustments when it's connected to the power line. So if your cable's connected, don't make the adjustments. Otherwise, unexpected things will happen. So just be aware of that. Okay, I'm going to go through those switches in a little bit more detail. So this is what's happening with the switches. So most linear power supply transformers have multiple sets of input windings, and I showed you that on my small toroid there. So it's got two sets of windings, and those two sets, in this case they're 110, mine happen to be on my toroid, they're 115 volt, and they're either connected in series like they are here, 110 in series with 110, giving us our 220 volts input, or they're in parallel. So I can see the wiring here wires these two in parallel, giving us the 110 volts. So that's what the switch is doing. It's reconfiguring the transformer inputs, taking those multiple windings and wiring them either in series or in parallel. And that's exactly what it says here. And we can see that in this diagram. So here in the diagram, I've got my little toroid again, two sets of windings, both of them 115 volt. That's what it says on the side of the packaging, and they're equivalent to these two here. And it depends how you wire them as to whether it's going to be set up for 115 or 230 in the case of my toroids, or whether I wire them in series or in parallel. But that's not the end of the story. Some of those power supplies we looked at had two switches, because sometimes you have sets of windings, but sometimes the windings may have multiple taps, and that's where you get the finer granularity settings. So let's look at that. So this shows one winding. And in this winding here, I've got my outputs. We can ignore those, but this is one of my windings. So I've got this, which is showing this winding here, and what it's got multiple taps. So I've got 0 to 100 volts, and I've got 0 to 115. And so I would have that on one winding. I would have exactly the same on the other. So they would be exactly the same. And then when you have your switches going in and out, you'll have switches which will switch the main windings and others which will switch taps. So if we look at our switch here, we've got at the bottom here, this switch is thrown to the left, and we can see that the left setting for the bottom switch actually switches the between the series and parallel, because at the moment this is set in series, and then when it's thrown to the right it will be the same as these, and it would set parallel. So this switch is setting whether the main windings are configured in series or parallel, and then the upper switch which is setting the fine level between 100 and 120, or between 220 and 230. This is adjusting taps rather than adjusting the windings, giving the finer granularity. So that's kind of the way it works, and that's what the switches are doing. Okay, the next part I want to cover is wiring the outputs. Okay, so we saw this in the live demonstration, so I just want to cover it here. So wire outputs together to give positive and negative outputs with respect to a common line. So you run a common line in as I had done on mine. The common line is shown in purple, and then connect the common line to, it can be connected to ground, or it doesn't have to be. You can just have a common line, and the common line is then wired to basically the common of the DUT. So when we look at these three outputs here, are they going to be positive or negative relative to the common line? Well, it's easy to work out. It's the opposite to wherever the common line is connected. So I've got the common line connected to the negative, so this is a positive output. In this case, it's connected to the positive, so this is a negative output. And in this case, it's connected to the negative, so it's positive output. And if we look at the results down here, output 1 is positive, output 2 is negative, and output 3 positive, all relative to the common line, and in this case also relative to ground because we've connected it onto the ground. That's great in this case, but I need more than 3 outputs. What do we do to get more than 3 outputs? We put another power supply in and then wire that up. So we continue the use of our common line. So add another power supply to extend the number of outputs. Wire it to the common line already in place. The common line's in purple. And connecting the common line to ground is optional depending on the DUT. So this is an optional connection here. So you could have that in or you don't have to. When we look at this configuration here, we actually have 1, 2, 3, 4, 5 outputs linked together, so they're all working relative to one another, and we also have a completely independent channel coming out as well. So that's how to wire the outputs. Right, and then next would be parallel and serial output modes. So depending on the power supply series, you will have some a guide on the bottom of the terminals here saying what is the connection for parallel and what's the connection for series. So you've got the parallel and series as switches here, and on different power supplies they're slightly differently labeled, but they're all do the same thing. So if I were to press the series, then my series output would be from the black through to the red. So that means this red and this black are joined together internally. And if I were to set the parallel button, then I've got the parallel on these two terminals here. So I will get twice the current out. And you can't press both at the same time. It won't accept that. On this power supply here, we have exactly the same thing. So we've got positive and negative for parallel on these two terminals, and then for series we are across these two terminals here, so that the other two terminals are actually connected together internally when that switch is pressed. So modern multi-output power supplies often have switches that allow the main outputs to be configured in series or parallel mode. Okay, and you'll have switches on there, one type or another. Parallel allows the configuration outputs to supply twice the standard current. So when you press the parallel button, what you'll do is you'll get twice the standard current out of these two terminals here. So you've got one output, but you've got twice the current. So if it's a 3.2 amp power supply, you'll be able to get 6.4 amps out of here. And that's what I've marked up here. And then if we look at the series mode will typically allow the configured outputs to supply twice the standard voltage. So it automatically connects the positive to the negative here. So when you connect up to the recommended connection points here, the negative and the positive, you're getting twice the output. And that's all that switch is doing when you connect it in series. It is literally linking these two together. Very similar to what we did with our common wire when we were wiring everything up. And that's exactly the same shown on this example of a power supply. Okay, let's go through a bit of power supply architecture. We talked about series and parallel, so let's look in that in a little bit more detail. So this is a very simplistic view. So in the linear, what I've got is the unregulated, so the power line source coming in, that goes through the switches, through the transformer, and then through, it says a series pass transistor, but I can assure you it's way more complex than that, gets filtered, and then it comes out as regulated power. Because the power supply is working at low frequency, it tends to be relatively large. Then in the switch mode, you have the line power coming in. That is then rectified, and then it goes through a switch and a transformer and filtered, and then that is output to your DUT. So the power is regulated with the transistor operating in its full on or full off, so it keeps the losses down. And varying the ratio of on or off defines the output voltage. So if we look at a basic diagram now, this is a basic of a linear power supply. So what I've got is my transformer. So this is my large transformer we saw beforehand, and I've got my two sets of windings, which are in either series or parallel, depending on our input voltage. In this case, the example was 240 volts. So for 240 volts, you'd have these in series. Running at low frequency, so this is either 50 or 60 hertz typically, rectified and out into the regulation electronics. Now this is shown in 3 pins, but I can assure you there's an awful lot of components in there. And I did go through our service manuals and had a look at some diagrams and thought, okay, I'll put a real diagram on here of what's inside the power supply. But to be quite honest, the diagrams are so large and it's on multiple pages, there's so many parts in there that it's very difficult to actually show somebody how it's working. So this shows it as 3 pins here, but there's a lot of components in there. And of course there's smoothing, and then you've got the output. Okay, and there's our switches which are configured. Now when we look at a switch mode power supply, we get our line power coming in regulated. So we've got a high voltage bus internally, and then we've got our high speed switch. We've got a step down transformer, and the PWM is affecting the on time and off time. So it affects the voltage which goes through the transformer and sets the output. Usually, the switch is usually running at above 15 kilohertz. So when you look at the linear power supply, back up here, you've got 50 or 60 hertz, and so you end up with a pretty large transformer. But as you go up in frequency, so your transformer diminishes in size to produce the same amount of power. Why is it greater than 15 kilohertz? Because if that frequency drops below 15 kilohertz, it drops into the audio range. So with some very early switch mode power supplies, you might sometimes hear a bit of a whistle. And if you did, it's because the switching is too low. These days, the switching could easily be, 50 or 60 kilohertz or even higher. So when we look at these transformers, we have a linear power supply transformer, so it's relatively large because of the low frequency, and then we have the switch mode, which is much, much smaller. And even though the switch mode transformer is much smaller, it will more than likely put out way more power than the larger linear power supply. This transformer is only 15 VA, so it's certainly not high power, but it's relatively large compared to the switch mode power supply transformer. Okay, so let's look at the different technologies. And some people are concerned about which power supply they buy, whether it's linear or switch mode. Some people aren't. So the reason for getting a power supply can vary enormously. Some people are very concerned that it's low noise and most responsive to load change. So low noise, those kinds of people would be maybe people working with audio amplifiers in that sort of arena where noise is very, very critical. Okay, and then people using switch mode may be more in the digital environment. So they're working with digital buses, microprocessors, those sorts of things, which have much, much higher noise immunity. So switch mode power supplies have much higher power density because the transformer is so much smaller and it's just so much more compact. It's also much lighter. And it's got a higher output noise level. We're going to look at that in a moment. And it has a slightly slower load change response time. So what do we mean by the response time? So typically a linear will be about 50 microseconds to recover from a 50% load change, whereas the switch mode power supply will be around about 100 microseconds. So if you look at it, you say, well, that's twice as long, yeah, but it's still very short time. So it's typically 100 microseconds. The modern day switch mode power supplies are almost as good as linear, so they're very low noise, very responsive. And other factors that may may affect your choice, obviously programmability, number of outputs, power, budget, etc. So I'm going to be looking at some aspects of this a little later on, but now what I'm going to do is switch over and talk about constant voltage and constant current modes. So we saw the demonstration of that, and hopefully that was clear as to what was happening. But just in case it wasn't clear, what I'm going to do is I'm going to clarify it again here. So what I've got is I've got a graph here. I've got amplitude on the y-axis and I've got time on the x-axis. I've got my voltage shown in blue. So I've got my voltage up here. I've got my current shown in red here. And my DUT load level is in purple. And then what I also have is my user set levels. So point 1 is my user set voltage level. That could be 9 volts, it could be 18 volts, 32 volts, whatever you've set it to. Point 2 here is my user set current level. That might be the maximum which the power supplies can output, or when I was doing the constant current on my example, I had it set to 200 milliamps, so it might be a user set level. So what's happening? We're in constant voltage mode. So our voltage is flat and at the user set level, and that is because the DUT is relatively low loading and the current has not hit our user set level. Now, when the current does hit the user set level, the current then stays at that level and the voltage drops. So it's happened because the DUT load has increased, and as that load increases, so the current hits its maximum level and the voltage drops down. As the DUT load drops, so the voltage will rise back up to the set level, and then if the load drops further, like this, then it'll go back into constant voltage. So you've got constant voltage mode for this section, constant current mode here because the load has increased and you've hit your current limit and your voltage then drops, and then it's switched back to constant voltage mode. You now have back to voltage, your current is dropping because your load is dropping. So you've switched back into constant voltage mode. So that's the way it works, and you can see how it's switching over. Hopefully that's clear, but I've got another couple of slides to clarify that. So if we look at constant voltage mode here, so we're using the same graph. So we've got the amplitude versus time, same voltage color, same current level color, and we've got points 1 and points 2, which are our user set voltage level and our user set current level. And in the constant voltage mode, the output voltage level remains at the user preset level. So this is remaining at the level you've set it to. Okay, and this is the most common PSU use model, and this is pretty much most of the time the way I use my power supply and the way most of the people I see use a power supply. They would set a voltage and the current would just go up and down as the load changes. So the current level is often set to the PSU maximum, but it can be turned down for protection. You don't want to, in my case, I used 200 milliamps because I didn't want to pop any of my load resistors. And the load never draws the maximum available current, because if it did, it would switch into constant current mode. Now, if we look at the constant current equivalent, in this case, we've got exactly the same color coding for the different waveforms in here. Point 1 is our user set voltage, our user set current. But in this case, we're in constant current mode. So the current level is being drawn by the DUT and it's staying at that level. And the voltage is therefore varying depending on the load. This is a less common PSU use model, so I don't see that many people doing constant current. Occasionally, but not very often. So user sets the current level and the voltage level changes with the load change. And as I did in my demonstration, if you've got a maximum voltage you don't want to exceed, you could set this at a lower level, so that rather than maybe your load dropping and your voltage increasing, damaging your components, you can set the voltage to a lower level so it would switch into constant voltage mode at that point and protect the components. So the load never draws less current than the user set level. If the current drawn falls below the user set level, the power supply will switch into constant voltage mode. Okay, now I want to look at some specifications, and then we're going to discuss some of these. So this table here is kind of interesting. It says choosing a power supply 32 volts. So these are 32 volt power supplies. So I've got 32 volts, 32 volts, 32 volts, 30 volts, 32 and 32. So why do we have so many 32 volt power supplies? And really the reason for that is in the detail. So let me show you a little bit of detail. So firstly, if we look at channel 3, here we look at channel 3, we've got some detail difference in here. In this T3PS3000, we've got the channel 3 switch between 2.5, 3.3 or 5 volts. In this power supply, we've got 5 volt is fixed. So you can't have 3.3 or 2.5. It's a fixed 5 volt. In this case, we have the switch levels and we've got 1.8 volt added to that as well. And in the case of this power supply, it's completely variable between 100 millivolts and 5 volts. Other differences in this range is that actually some of them are 4 output. So some of them are 3, but we also have 4 outputs. That's something slightly different. And we've got the third and fourth here. So we've got a 15 volt and a 5 volt, 15 volt and 5 volt here. So you actually have 4 outputs here. The other thing to look at, which I'm not highlighting with any red boxes, is also the amount of current you get out as well. Obviously the 32 volts are pretty much all the same, but when you come to channel 3 and channel 4, they can vary quite a lot. 3.2 amps, 5 amps, 3 amps, 1 amp out of each, 1 amp out of each. So there's a bit of difference there. The other thing is to look at the difference between the linear and switch mode. And that's something we have spoken a lot about, looked at diagrams, things like that. So let's look at the specification. You can see it in here. So the linear power supply is lower noise. So we can see that from 5 hertz to 1 megahertz, you've got equal to or less than 350 microvolts RMS, whereas the switching power supply is less than 5 millivolts. So it's still very low, but it hasn't got that really low level that you get with the linear power supplies. And the same with channel 3. And then you've got the recovery time. And this is what I talked about earlier on, that the linear power supplies tend to recover from a high load change quicker than the switching. So I've got 100 microseconds compared to 50 microseconds, and that's with a 50% load change. Okay, other things to look at in there may be the total power you can get out. So in this case, most of these are 200 watt, and I've got one here that's sitting at 375. So that's kind of interesting. There's a lot more power. Or it may be the fact that some of them can be configured they all do the series and parallel. We've got the series and parallel in here, 64 volts in the series and 6.4 amps in the parallel. So we can see that along here. And then I've got one here that's actually 120 volts at 3 amps or 30 volts at 12 amps. So even though there's a lot of power supplies that look on the face of it, without looking at the detail, they look exactly the same. There's actually lots of subtle differences in here, which need to be thought about when you're making your choices. Another one might be programmability, for instance. Is it programmable or not? I don't need programming. Okay, well, I can have any of them if I don't need programming. But if I do need programming, then I've got to make sure I make the right choice. Obviously, we don't just have 3 and 4 output, we have a whole range of 1 and 2 output power supplies as well. Okay, some of those specifications we saw were in there. I should go back and look at that actually. Let's just pop back a couple of slides. We also have in here, we have line regulation and load regulation. Okay, and so what I want to do is talk about that. And these are in the voltage mode, and then I've got line and load regulation in the current mode. So I'm going to talk about those now. So what is line regulation? So constant voltage line regulation, so we're in constant voltage CV mode now, is the ability of the power supply to maintain a constant output voltage regardless of the changes to the input voltage. Okay, so we've got a little formula here. So V out over V in as a percentage, and this is the specification for all of those power supplies that we were looking at. And what you'll notice in the specifications is they're all pretty much the same. There's very little difference between any of them. They're all very, very low levels. And also there is not just a line regulation for constant voltage mode, there's also a line regulation specification here, the top line here, for the constant current mode. So what happens in constant current mode if the line voltage changes. So let's look at this graphically so you really understand what's going on. So if I look at this, I've got a waveform here, and this is my line input of 120 volts at 60 hertz. So I've got 120 volts at 60 hertz, and I've used what's called a measurement gate. So I'm measuring from this end of the screen to this dotted line here. It's not a cursor, it's a measurement gate. So I'm measuring in this section here, and that's where I've got my 120 volts and my 60 hertz. Okay, now what I can see, if I look very carefully at this, I'm sure you can see it, is that you've got a slight change in height from here to here. So that the height has changed, it's gone down in amplitude. And so when we move the measurement gate over, and I've moved my measurement gate to this end now, I can see, if you can read this out, hopefully you can, that my voltage at the second half has dropped to 110 volts at 110.77 volts, and still 60 hertz, of course. So I've dropped from 120 volts input to my power supply to 110 volts input to my power supply. What effect is that happening? So this is what line regulation is. So the line drops from its nominal value momentarily to a lower value. What effect does that have on the output? And that's what that specification is talking about. It's the specification of the change in the output relative to the change in the input. And as you can see from those specifications, that's very low. So let's look at load regulation. So what is load regulation? And that is the change in the load. It says here voltage load regulation is the ability of a power supply to maintain a constant output voltage level regardless of the changes of the power supply load. So as the load changes, you've got the regulation for it here. And that load change, when it's done as like a calibration test, the load change is a 50% load change, and you also have a recovery time, which was the 50 or 100 microseconds. And you have that specification for both the constant voltage and constant current. So that has a load regulation as well. So the specifications for all of those, and you'll see in there, they're all the power supplies are pretty much the same, pretty tight specifications in there. So if we look at that graphically, what I've got here is I've got my voltage, and I'm using a fairly low voltage because I'm just using some of my loads in here connected together. And what I've got here is I've got my ground level here, and this is my voltage in yellow, and it's 2 volts per division. So I'm measuring here a mean level of just over 6 volts. So that's the level I've got here of C1 being yellow. Now C2 is my current, and that's 1 amp per division. So I'm starting low, and then I'm throwing my switch. And this is it's either 3.2 amp or 3 amp output, whichever one it was. I think it was a 3.2 amp output. And so I'm actually throwing it more than the specification for this particular test is 50% instantaneous load change. So I've gone from 0 to 2.8 amps, and I've got a rise time here of 87 nanoseconds. So we can change that load and see what happens. What I've also got is on channel 1, I've got a peak-to-peak deviation of 8.24 millivolts, and that's going to be here. So the power supply didn't know that there was going to be a large load change, so of course it's not prepared for it. So there's going to be some sort of deviation. So I've got the deviation, and I could also measure the specification, which is the before voltage and the after voltage, and I could compare those against the specification. Okay, so we can look at that in detail. So I've zoomed in here, and so we've got a zoom of our trace we were looking at, and now what we can do is we can see the current coming up, we can see the voltage response, the deviation here, and we're at 400 millivolts per division on the voltage, and we're measuring that 824. So when we look, that should be just over 2 divisions. So when we look at the height of it, it's yeah, it is just over two divisions. So 824 millivolts is what we're seeing here. So it's the deviation of this lower peak and this upper peak from each other. It's actually not from the mean value that's in here. It's actually deviation from between the lower and upper peak, because I did a peak-to-peak measurement here. And if we look at that in a little bit more detail, we can see the current coming up, and we can just see that in more detail. So I've zoomed in a little bit closer to show that. Okay, and then what I'd like to cover now is sense terminals. What are sense terminals? Some power supplies have sense terminals, some don't. Most of them don't, particularly if they have multiple outputs, because sense terminals are another set of terminals and they take up more space on the power supply. So it's usually single output power supplies have sense terminals. So let's look at how a power supply works. We've got the power supply here. We've got it connected to our DUT. We've got 32 volts, which we've set here. Probably I wouldn't set 32 volts for this DUT because I know this is low voltage. But that 32 volts, which I've got set on my screen here, is actually at the output terminals. It's not here on the connection to the board. So what's the voltage here? Well, I may need to use a DMM, or what I could do is I could use sense terminals. And sense terminals connect to the DUT point of connection. They come back into the sense inputs to the power supply, and so you move your 32 volt output voltage from the output terminals here to the connection on the board. Now, usually this is really only much of a concern if you've got a lot of current. If there's you know, the voltage is 32 volts, but you've got very little current, then you're going to get very low cable losses. So the ways around this obviously is to use sense terminals. Increase the thickness of your cables is another way around it. So this is the feedback, and that's what the sense terminals do. So what do you need to think about when you're purchasing a power supply? So there's many different things you need to think about. What's the maximum voltage, maximum current and power that I need? Do I need linear or switching, or is it not important to me? Because if it's not important, you've got a wider choice, okay? You've got a wider choice. Other things may be important, like programmability or budget, those kinds of things. Do I need sense terminals? There are things which some power supplies have, some don't. Very few people use them, to be quite honest. Most people just use the standard front terminals. How many outputs do I need? Between 1 and 4. And this is a much more interesting question, because quite often people will move towards a higher number of outputs. I certainly do. You can do a lot more with a 4 output power supply than you can with a 1 output power supply. And then other things like is remote control important? It gives more flexibility, but it costs something, and if you don't need it, then you can save money and not have it. And that's the end of the presentation. Thank you for watching.